The following video is on the limit definition of the derivative. Recall that f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h, provided this limit exists. So let's do some examples of this. If the function f of x is 2x squared, let's try to find the derivative f prime of x. So rewriting the formula, we have the limit as h goes to 0 of f of x plus h minus f of x over h. And notice that f of x plus h is going to be this function f of x, but instead of x, I'm going to plug in x plus h. So I'm going to have 2 times x plus h squared. Then we have minus f of x, so that's going to be minus 2x squared all over h. So if I FOIL out the x plus h squared, I get 2 times x squared plus 2xh plus h squared. Then I still have the minus 2x squared all over h. I'm now distributing the 2 through the parenthesis. And now we see that the 2x squared and the minus 2x squared cancel, and everything that's left has an h in it in the numerator. So I'm going to factor an h out of every term in the numerator, and now the h in the numerator cancels with the h in the denominator, and I'm able to do direct substitution. So I'll end up with 4x plus 2 times 0, or 4x. So the derivative of 2x squared is 4x. Remember, the derivative tells us the slope of the tangent line to the function at any point x, and so 4x is going to tell us what the slope of the tangent line is at any value x. Let's try another example. Let f of x equal 1 over x. Once again, I'm going to find the derivative using the limit definition. So the limit as h goes to 0 of f of x plus h minus f of x over h. And this time, my function is 1 over x, so f of x plus h is going to be 1 over x plus h. So everywhere that I saw an x in f of x, I'm replacing that x with x plus h. So I have 1 over x plus h minus 1 over x all over h. And in order to simplify this limit, I'm going to need to find a common denominator for the numerator. So I'm going to multiply the first fraction by x over x, and the second fraction by x plus h over x plus h. And now I can rewrite it all as a single fraction in the top, x minus x plus h over x times x plus h, all of that over h. And distributing the negative sign through, I see that my x's cancel. So I'm left with negative h over x times x plus h, and to get the h out of the bottom, the h in the bottom is the same as thinking about it as an h over 1, so I can replace that with multiplying by the reciprocal, which is 1 over h. Now we see that the h in the top cancels with the h in the bottom, and I'm left with negative 1 over x times x plus h. If I do direct substitution, I get negative 1 over x squared. So the derivative of 1 over x is negative 1 over x squared. Once again, the derivative tells us the slope of the tangent line to the function at any point. So if I wanted to find the slope of the tangent line to my original function, I would just plug in the x value into this formula, negative 1 over x squared. There's other notation for the derivative. The reason for this is because calculus was simultaneously discovered or invented by 2 different mathematicians. The first is Sir Isaac Newton, who lived from 1642 to 1747. He invented calculus in 1666 at age 23 over his fall break, but he didn't end up publishing it. The notation that he used was f prime of x. Simultaneously, another mathematician named Gottfried Leibniz who lived from 1646 to 1716. He also invented calculus a little bit later, 1674. He published it, though, unlike Newton, in 1684. And the notation that he used was d by dx of f, or dy by dx. So even though it looks like a fraction, we read it as dy by dx. So the reason that we have these two different notations is because calculus really was invented by both of these people, and in some cases it'll be easier to use one person's notation than the other. The last few years of Leibniz's life were spent trying to clear his name because Newton was trying to claim full credit for the invention of calculus. And although Newton did discover it first, Leibniz did discover calculus entirely on his own, and he also made some contributions that Newton was unable to make. Unfortunately, Newton had a lot more power and wealth and clout, and was able to, at the time, claim full credit for inventing calculus. So when does a derivative not exist? There's three ways that a derivative cannot exist. The first is at a cusp or a sharp point, just like we see. The second is at a vertical tangent line. Notice that that's different than a vertical asymptote. A vertical asymptote is a point where the curve is going off to infinity. A vertical tangent line is when the tangent line is going off to infinity. So at that point, the tangent line is going to be straight up and down. And the third is at a discontinuity. So, let's see. Note, however, that if a function is differentiable, in other words, if we can take the derivative, then it must be continuous at that point. So this seems to be confusing. We said that a derivative does not exist at a discontinuity, but if a function is differentiable, then it must be continuous. So we're going to talk about the proof of this in class. But what's happening here is we've actually taken the converse of the function. So we can find a function that's continuous but not differentiable. Notice that this function with a cusp is continuous. I can draw it without picking up my pencil, but we said that if a function has a cusp or a sharp point, it's not differentiable. And looking at the Venn diagram, we have the world of all continuous functions, and inside it, we have the world of all differentiable functions. So everything that's differentiable must be continuous, but not everything that's continuous must be differentiable.